Okay, so today I will talk about the extending instruction sets. As we know, so far we learned 9 instructions for this processor, and today we are discussing on some new instructions. The first thing we should notice that so far all we discussed were like a direct addressing instruction. What does it mean? It means that in the instruction we have the address of the data. You remember, for example, load X. Here's what I'm telling now. It's part of your exam, so listen carefully, because in the exam there was this kind of questions. Load X, what does it mean? Load X means that go to address X and data is in address X. We call it direct addressing. Direct or direct addressing. So we just provide the address directly in the instructions. But we have another type of addressing which is very important, and it is called indirect addressing. What does it mean? It means that the address provided in the instruction is the address of the address of the data. The address of the address of the data, not the address of data. Okay, so in indirect addressing, we like mention the address of the data. If you have programmed like in high level language, you know how does pointer works. So like pointers are the same type of like addressing. They point to the address of something, not the address of something directly. Okay, and I will show it in the example. So let's say we have the memory. We have the memory, and here is address 100, and let's say here is address 200. And the data in address 100 is A. We call it AA, just as data. And the data in address 200 is called BB. If I say load 100, it means that the data is the data is the data is located in address 100. The data is located at address 100. And let's say we have another address 150, and inside we have data 200. But if I say load I, it means indirect. Load I 150, what does it mean? It means that the address 150 is the address of the data. So it first goes to address 150. Inside it is 200. 200 is address of the data. So the data will be BB. So data loaded to the accumulator will be BB. So it's a different in different in direct and indirect addressing. So can you tell me what is the content? What would be the content of accumulator if I just use direct addressing of load 150, not indirect? Number 200. Number 200 will be loaded like to the accumulator, okay? But if I say load I 150, it means that inside the address 150, we have address of the data. Is it clear? So it's obvious that the micro operations will be more complicated than like the indirect addressing, because we cannot just refer to the address of the memory and grab the data. We should go to the address, get the new address, move to the next location and grab the data. Okay, so for direct addressing in for the load X, for direct addressing, we would say just put X in MAR, the content of MAR moves to MBR, and MBR moves to accumulator. This one is a load instruction micro operations. How many micro instructions, micro operations? Only 3. Okay, but for load IAX, load IX, which is indirect addressing, we need to have 5 micro operations instead of these 3. Which micro operations? First, we load the address X in the MAR, get the content of the that memory location, put in MBR. The MBR is not the address, is not the data. At this moment, it's not data because it's indirect addressing. MBR again moves to MAR. The content of MAR moves again to MBR, and this time MBR will be moved to the accumulator. So we have the data in our example. So let's say if we had 150 in previous example. No. The reason I said the RTL for load is, I didn't say it's not correct. I said it's not complete. It's not complete because this RTL we see here is only for like it doesn't consider it doesn't show the program counter, because we know that the complete RTL at the beginning we need to load PCI, so the PC program counter, to the MAR, and first. So let me tell you the answer. This part is decode. This part is execution. Let me MAR, MBR, decode and execution part. It doesn't. It's not included the fetch part. The fetch part also needs micro operations. The fetch part just we already discussed it, I think, in the last week. The fetch part put the PC inside the MAR and grab the instruction, put it in IR, and from IR move it to MBR. Let me go back to previous slides to make sure that we discussed this. Okay, here. Exactly, yeah, here. This one is the complete. Let me find a load here. This one is the complete instructions, which I mentioned. Okay, so the complete micro operations consist of the fetch part as well. Okay, fetch part is like moving PC to MAR, grab the instructions, put to IR, and increase the PC. Which this one was not part of, not part. This one is not shown here. It's not shown here. So it's the reason I said it's not complete. Okay, so let's go back to our example. If you remember, our example was, where is our example here? Our example, this example. So MAR, X goes to MAR, 150 moves to MAR. The content of 150 goes to MBR. What is the content of MAR? 200. Moves to MBR. So MBR has 200. MBR has 200. That value moves to MAR again. The content of MAR this time is BB. BB moves to MBR, which is BB, and this data will be moved to the AC. Okay, so this one is like the indirect addressing cycle. And all of this, which is shown here, is decode and execution phases. It's not included the fetch phase, because fetch phase is same for all instructions. So we don't have to show it in all of them. So fetch phase is like putting PC in MAR, the content of MAR to IR, and increase the PC by 1. This one is the same for all instruction, because grabbing the date instruction from the memory. Okay, any question? Now that we learned, load indirect X, let's see what is load store indirect X. Store indirect X is the same thing. It says that it store the accumulator in a location which the address of that location is in address X. It doesn't. It says that do not store the accumulator in address X. Go to address X, get the information, get the address, and store the accumulator in that new address. So if we discuss and we look more closer look to store IX, we see that the address moves to MAR. The content of MAR, which is like the location of the address, will be moved to MBR. MBR again moves to MAR, and this time accumulator, which is data, will be moved to MBR, and MBR will be placed in memory location of MAR. So this one is how does a indirect addressing work? Okay, so any question? What about add? We have add I x. It's the same story. Add x, if you remember, add x means that get the data from address x, add it with accumulator, and place the result in accumulator. But add ix says go to address x, find an address, go to the new address, grab the data, add it with accumulator, and place it in accumulator. Okay, and here is like how does it work. We like place the like indirect address in MAR, indirect address in MAR. MAR content moves to MBR, so we can say at this stage MBR has direct address. Then the direct address moves to MAR. The last one is the data moves the data moves to MBR. MBR will be added by AC with AC, will be added with AC and store in AC. So this one is the like definitions or explanation of this instruction. Okay, so if we want to build add I instructions, okay, add I instruction by using other instructions, we can combine these two instructions, load ix and add x. If we combine these two instructions and put them next to each other, like both of them like act like an add I. So we can make an add indirect instruction by combining these two instructions. Okay, so I would say add indirect x is equal to these two line of instructions. Load ix, add x. If we combine these two instructions, the output is the same as add ix. Any question? And by the way, you should know that indirect addressing is more important than direct addressing. 90, maybe even more, 95, 99. 90-something% of like the addressings are indirect addressing. Okay, because all the programs are based on the pointers, address pointers, and so all of them work with indirect addressing. Okay, so indirect addressing is much more important than direct addressing. Okay, the next instruction that we want to discuss. So far we had 9. We learned 3 more, and now we want to learn the next one, which is JNS. JNS, which is very important for like for routines, for call, you know what's the call, how we can call a subroutine, a procedure in like programming. When we want to call a subroutine or procedure, we always use a call instructions. JNS is the same kind of instruction. What does it do? It JNS. Let me tell you what is JNS. JNSX. Okay, X is an address. Let's say this one is the address, and here is address X. Here is address X plus 1, X plus 2, and so on. JNSX says, please save the value of PC, whatever is in the PC, in address X and jump to address X plus 1. Save the value of PC in address X and jump to address X plus 1. A jump is jump. We know what's jump. Jump like jumping to an address. So what is the jump? Jump is like loading the PC with like X. Jump to address X means that the load PC with address X. So, but before jumping to X, we want to save the return address in location X. And here is RTL. Here is RTL for JNSX. Okay, let's see how does it work. Okay, so let me just write in the left side. PC moves to MBR. Okay, so there is no explanation. We know what's PC moves to MBR. X moves to MAR, the address. This part, the third line, MBR will be copied to MMAR. What does it mean? It means that the PC will be copied to address X. Okay, so MBR to MMAR is like means that PC will be copied to address X. Okay, then address X will be moved to MBR. 1 will be moved to accumulator, and MBR will be added with accumulator. So it means that MBR will be added by 1. What is the content of MBR? Can you tell me? The content of MBR is X. So X will, so what is the value of AC at this moment? X plus 1, very good. And so the last line, PC, oh, the last line, this one is mistake. Fix your like PowerPoints. This one should be AC moves to PC. Okay, this one is like a typo. So correct this one in your slides. Okay, I couldn't correct it because it's like a picture. It's a picture. So, but have a note somewhere that this is not PC to AC. It's AC to PC. So X plus 1 will be moved to accumulator, and last line, PC will get the value of X plus 1. Even the PC gets the value of X plus 1, it means that the program will continue from address X plus 1. Okay, so why we need to store PC in address X? Anyone knows? Why we need to save PC in address X? We can go back. Yeah. Sometimes we want to do some like a sub program and come back to the original instruction and continue from the location we left. So we need to have like the value of PC. We don't want to lose that value. Okay, so it's the way we keep the value of the original value of the PC in location X and continue. And if you remember for interrupts. For the interrupts, if you remember, I want to use this. I want to use this white screen, and I hope that it doesn't disappear. Uh, if for subroutine for interrupts, I said that we have different parts of the like memory. Like this one is a memory. This one is interrupt. And let's say here is x, address x plus 1. Here is address y plus 1. And these are interrupts. For example, here is interrupt number 1, interrupt number 1. Here is interrupt number 2. Those two interrupt procedures. Let's say one of them is for dividing a number by 0. The other one is like low battery or any warning. And we are in this location. We are in location 100. Okay. And we get an interrupt. If we want to jump to interrupt X, which instruction we should use to jump to interrupt X? JNS. JNSX. JNSX, in fact, jump, we lost all those picture, but that's fine. It was almost the end of it. So if I say JNSX goes to X, so the like the return address in X, and it starts from X plus 1. So the interrupt program has to be started from address X plus 1, not address X, because address X is reserved for the return address. Clear?
Then the last instruction of the interrupt will be to go back to X and then
Exactly. The last instruction, like go to X, get the address and jump it back to that. Yeah, we will see it. Okay, I'm not going to discuss it, explain more at this moment, because in the next few slides we will discuss that point. But it's a very good question. Yeah, the last instruction of any interrupt or any subroutine is like getting to X, getting the return address, and jumping to that address. Okay, so the next instruction, we have one more instruction, which I think it's last, it's not here. Let me just see. The next instruction, which is missed in like in the slides, but we have it in the textbook, is called jump in Directx. Jump, GUMP, indirect X. It is different than JNS. JNS, of course, is like JNS is like a store the X in store the PC in address X and jump to X plus 1. But what does jump indirect X means? It means that like indirect jump. It says go to address X, get the value, the new address, and jump there. And it is exactly the questions that you ask about the last line of each interrupt. As at the last line of each interrupt, we need to have a jump in Directx, because we need to go to X and get the PC and jump to the PC. Let's show the macro operations on RTLs for jump in Directx. MAR, X goes to MAR, MMAR goes to MBR, and MBR moves to PC. Do you remember what was the RTL for jump X? No, just the RTL, I mean micro operations. Like what I wrote here. X go to MAR, and MAR go to PC. Okay, do you confirm or any other answer? Just go back to your notes and find it. I want you to just check your notes. The reason I'm asking, I know the answer, but that's fine. I'm not saying this one is wrong or right. Just I want you to just check your notes and okay. Hmm? Not skip condition. It is not in the like. It is not in the notes. So yeah, which slide is that? Yeah, I don't see it here. Okay, so I think that one is also it's not, but that's fine. So this one is correct, or where we okay, so this one is correct, or also we can say the load value of X to PC. Okay, both are correct. That's fine. So we can say load the value of X to PC or put X in MA. But I believe this one should be like the left side should be easier because we directly move the X to PC, not to MAR and from MAR to PC. Okay, so but the next instruction after jump indirect X, which is different than jump X, is clear. The clear is different than halt. Halt just to stop execution of the program, to stop there. But clear just set the value of accumulator to 0. Okay, that's it. Just set the value of accumulator to 0. I believe that it's the like easiest, the simplest instruction we have. Just simply set the value of accumulator with 0. Okay, questions? And we done with our instructions, and now we want to see some examples. Okay, let's just write some programs together. I forgot to print it out, so I have to go with this slide. Let's see what does this several line of programs do. Okay, let's just analyze this program together and to see what does it do. We have some labels. I want to like put a circle around these labels. Do you know what's the label? Label is same thing we use when you program in assembly, and assembler converted to like machine language. Okay, so we have lots of labels, and these labels are for specific addresses from 111 to 116. So address 111 is labeled ADDR. The content is 117. Okay, we want to work on this program together and see what does this program do. Label next is on address, refers to address 112 and has a value of 0 and so on. Let's start from first line of the program. Load address. What does it mean? It means that load. Okay, can you tell me after running the where to the accumulator? Yeah, load 117 to the accumulator. So accumulator will be equal to 117. Okay, so then store next. What does store next means? Store next means no. Next is a label. Which value? The value in AC. It's not 0. Store the value in AC. Store the value in AC at which location? 112, which is next. So at this moment, 112 will have at value 117. After running the second line, the address 112 will include 117. Okay, it's very important. Just listen and learn, because we have 4 more programs, and after that you will have projects to do, and you are responsible to write this kind of program. Okay, so let's move to the third line. Load num. What is num? Num is like address 113. What's the value of that? 5. So it means that accumulator will be equal to 5. Any question? Okay, next line. Subtract 1, address 1. Address 1 has a, which value is in address, address 1 is 1. Subtract means that subtract accumulator from that value and place it in accumulator. So can you tell me what's the output of this line? Which location? Accumulator will have a number 4. Okay, so accumulator is number 4. We reach to this point. Okay, let's move on. Store CTR control. CTR. It means that number 4 should move to control address. Control is just an address. So CTR will have address 4. Any question? So okay, so we move line by line by line to see what does this program do. Because definitely we cannot say what does this program do by first look. So we need to analyze it. Okay, so what we're doing now, we're analyzing this program to see it. And I'm looking for an answer from one of you. Tell me when we reach almost at the end, tell me what does it do, this program. Okay, so 104, I said that the store control, so store control says that the address 150 has a value of 4. 105, load sum. Let's go to address sum. What is the value of address sum? 0. So what is the output of this instruction? 0 where? Accumulator is equal to 0. So we say accumulator is equal to 0. Let's move to the next instruction. Add indirect. This time indirect come in the game. Okay, indirect instruction come in the game. So add indirect next says go to address next, get the address 117 and get the value of 117, which is 10, add it with the accumulator, which is 0, and place it in the accumulator. So after running this one, accumulator has a value of 10, not 0, 10. It's not times, 10 plus 0. Okay, so 10 plus 0 is 10. Any question for this part? So you see how useful is indirect addressing. Okay, so we need to have. Let's move to the next instruction. Store sum. It means that accumulator should go to sum. So accumulator has a value of 10. Go to sum. What is the current value of sum? 0. So it will be updated to 10. Let's move to the next instruction. Load next. What is the value of next? 117. So accumulator is 117. 117. Add 1. We know that address 1 has a like 1. So accumulator will be equal to 118. Store next. Store the accumulator in address next. What is the address next? Is 117. So this time we'll store 118. So 117 will be erased, override with 118. Okay, let's move on. We reach to this point. Load control. So AC will be equal to 4, subtract 1. So AC will be equal to 3. Store control. So control will be 3. Let's move on. This line, 10E. Skip condition 0, 0, 0. Skip condition 0, 0, we need to check. We need to check. Skip condition 0, 0 means jump next instruction if accumulator is equal to 0. Okay, what's the value of accumulator? 3. So should we jump next instruction or no? No. So we go to 10F. What does 10F say? Jump to loop. So let's go back to 105. Okay, this time I put a circle around it. 105. 105 says load sum. So what is the value of sum at this time? 10. So 0 will be updated by 10. Add indirect next. Okay, add indirect next. So we go to the next. Next, this time is 180. 180 has a value of 15. The 15 will be added by 10. Total is 25. 25 will be placed in accumulator to accumulate. This time 25 is an accumulator, and go on. If we continue, we reach to this point that we subtract the 1, and again accumulator will be in line 10C, will be 2, 1, 0. How many times we repeated this loop? 5 times. 5 times we repeated to this loop, and every time we add like the sum, this address with with one of these addresses. Okay, so at the sum at the beginning was 0, then it becomes 0 plus 10 become 10, then 10 plus 15 become 25, 10 25 plus 2 27, yeah, but then 27 plus 25 is 52, and finally 52 plus 30 is 82. Okay, it's clear? So I repeated 5 times. After 5th times, the 5th time, what's happening? When we check the skip condition, this time accumulate has a value of 0. So we jump the next instruction and we halt. And what is the output of this program? The value in sum will be the total of these 5 addresses. Value of sum will be the total of these addresses. So what kind of program is this? It just adds like 5 numbers located in part of the memory. Is it clear? So I post this lecture online, so I hope that it's a recording, and so you can just go. And I just repeated one. I just went over it 1 time because all 5 times is same, repeating. But the only thing was important. We should know that line 1, OC, line 1 OC, like in the left side, 1 OC, which is subtract. They're like the subtracting, like the control by 1. So control starts on 5, and 5 times it's so can you tell me if we want to add 10 numbers instead of 5 numbers? 10 numbers. What modification we need to do in this program? It's correct. It's control is equal to the not control, because control at the beginning is equal to 0. The for control num has to be 10, because num moves to control, and after that control just reduces by 1 every time. So at the beginning we have num. Okay, num moves to the control, and after that like the control gets the like the control of this program. Okay, so very good answer. And any other question? Okay,